question I made a bonus yesterday. This will not be on your test on Monday. Cross it out. So don't have to worry about this one. All right, so we're going to start today with average rate of change. Average rate of change is a fancy word for what? Slope. So that's what we want to be thinking about here. You are given two x's. So we have -3 and -5. And I can find the slope if I know the y's that go with them. So that's going to be your first step, is to plug these numbers in to our function and get the y's that go with them. So h of -3. -3 to the third minus 4 times -3 squared plus 1. So let's see, that's going to give me -27. -3 squared is 9 times -4. It's -36 plus 1. So grand total of -63 plus 1, -62. And again, you'll have a red calculator for stuff like that. Okay. And then same thing, we're going to plug -5 in. -5 to the third minus 4 times -5 squared plus 1. So that's -125. 25 times -4. So -100 plus 1. So that's -225 plus 1. -224. Okay, so that's the second half of my points. -3, -62, -5, -224. And now all you have to do is your slope formula. y2 minus y1 over x2 minus x1. -224 minus -62 over -5 minus -3. Oh, and what does that give me? -162 over -2, so positive 81 is my answer. Okay. Any questions on that one? Okay. Next one is a difference quotient. So this is a formula you need to know. I'm going to go ahead and put it on here. I'm going to write it with function f, but remember our function can be named anything like function p. So your difference quotient formula was f of x plus h minus f of x all divided by h. So we talked about 3 parts to this problem. Plug in x plus h and simplify, then subtract the original function, and then divide by h. So when we did them in class, and here it's function p again, not function f, we started by just doing that first part. Plugged in x plus h and simplified. Okay, so we're taking the x out, we're doing substitution, x plus h in its place, make sure you use parentheses. The negative is not inside the parentheses, negative. Quantity, x plus h squared plus 6 times x plus h plus 7. And then we've got some simplifying to do here. Remember, you always FOIL before you distribute. So I'm going to leave that negative kind of hanging out there, and I'm going to FOIL out my parentheses first. If you need to, think of it as x plus h times x plus h, first, outside, inside, last. First terms are going to give us x squared. Outside terms are xh, and my inside terms are also xh. So that's 2xh. And then my last term's h squared. I'll just bring everything else down. Okay. Now I can distribute. And that negative is just going to change the sign of everything in that first parentheses. Multiply 6 through my second parentheses. Bring down my 7, no like terms. Okay. So now we just add on the couple other pieces. We already did that f of x plus h. The next part of the instruction says subtract f of x, which just means subtract the original function. So I'm going to put minus. I'm going to put a parentheses, that's important, and I'm just going to put the whole original function in that parentheses. Negative x squared plus 6x plus 7. And then the last piece is to divide the whole thing by h. So what you see on that third line there, that's really the whole formula used now. I've got my x plus h minus f of x all divided by h. We just have some simplifying to do. First thing you're going to do to simplify is just distribute your negative through that second parentheses. So let me do this actually a different color. That's going to look like negative x squared minus 2xh minus h squared plus 6x plus 6h plus 7 plus x squared minus 6x minus 7 all over h. Now, if you're doing this right, anything that has that came from the original function should cancel. Like you have a positive x squared and a negative x squared, those cancel. I have a positive 6x and a negative 6x, those cancel. And I have a positive 7 and a negative 7 that cancel. So it leaves me, should leave me, with all the terms that have h's in them. And then the whole thing is divisible by h. So because every single term in this fraction has an h, I can reduce the fraction by h, which means I can take one h or divide one h out of every term. If I divide one h out of every term, I'm left with negative 2x minus h plus 6. And on the denominator, I would have a 1 that's in front of that h, but usually if just 1's in the denominator, we don't write it. So what you see there is your difference quotient. Any questions on that one? Any of the little pieces and parts that go into that formula? Okay. Next one, write a function for the piecewise graph shown below. Now, one of these, this graph is not quite perfect, should be an open circle. I'm going to make the one at the top an open circle and the one at the bottom, because if they're both closed circle, it wouldn't actually pass the vertical line test. We know that. Okay, I'm going to start with the line. Okay, I have a point on the end there, and I can actually label that point. 3, 5 is a point on that line. And I can pick another point, doesn't matter which one. Looks like I have 5, 7 also. Okay. 2 points on a line are all I need to find the equation of that line. And we're not going to worry about the fact that the line stops at this point. We're just going to find the equation of the whole line, and then we'll say where it needs to show up at on the graph, okay? If you have 2 points, there's 2 things you need for the equation of a line. You need a slope, and you need a y-intercept. The slope, you should pretty easily be able to just count from this, rise over run, or you can use the slope formula. You should be able to see that you're going to rise 2 and run 2. 2 over 2, my slope is 1. Okay. Then you have either 2 choices depending on what this graph looks like. This one, it's not terrible. You could just use that slope of 1 and work backwards and see that if I extended that graph, it's going to touch the y-axis at 2. I know my y-intercept is going to be 2. Now, let's say you have like weird fractions or it's not exact necessarily, and you wanted to solve for b. We know how to do that. You can use your y equals mx plus b, fill in the slope, which we know is 1, and then fill in either of those points. Like I could use 3, 5. My y is 5, my x is 3, and you can see there if I solve for b, I will get 2. So you can solve for it. That's obviously more exact, but if you have nice pretty numbers like this one, you could kind of work backwards and visualize it. It's not a bad thing just to visualize it anyway to make sure whatever answer you get for b is reasonable. Okay, so the equation for the line, and I'm going to just start writing my function notation here with my piecewise. I've got 2 pieces, so 2 pieces, 2 rows I'm going to have here. My first one is 1x plus 2. That's the equation of my line. The second one is going to be the equation of that parabola. Now, what's the basic equation of a parabola? Y equals x squared, okay? So you're not really meant to like solve this. You're just meant to kind of realize the basic function has moved where? 2 to the right. And if I want to move something 2 to the right, what do I do to its equation? Minus 2 inside or outside? Inside. So it's going to be x minus 2 squared. That's all you have to do for that equation. Okay, so it's just our parent function, and we're applying a couple transformations to look like what it should. Now, the only thing I'm missing here is I need to restrict the domain a little bit. Let me give myself maybe a little more space. Move that down a little bit. There we go. Okay, so for each of those, I need to say the x value that it occurs at, or it shows up at. So for the line, what's the first x value that that line shows up at as I read the graph from left to right? X equals, think about this just like a domain question. What's the domain of that line? It's 3 to infinity, right? As far left as it goes. So that's my restriction. X has to be greater than 3. We write these with inequalities. It's greater than, not equal to, because it's an open circle. If it was a closed circle, it'd be equal to. And then the parabola is everything less than or equal to 3. It's to the left of 3, and there's a solid dot, so I see equal to. Okay. What questions do you have on that problem? That puts a lot of different things together. All right, flip it over. Oh yeah, sorry, go ahead.
So under the line equals 2, you always start with x squared and then it's 1 line.
If it's a parabola. Now, on the test, it might be 2 lines, and you just might do the same thing again. So I'm not going to give you anything more than a line and a parabola, though. I wouldn't worry about any of the other shapes. Okay. Anything else on that one? Okay. All right, graphing the piecewise function. So this is just kind of the opposite of what we just did, and then we're going to state any values where it's discontinuous. Okay, if you guys remember doing these, we set up tables. This is the one where you guys actually had a ton of practice problems on a worksheet that you did for homework. Okay, we have 3 pieces. So I'm going to make kind of 3 parts of my table, bless you. So the first part is going to just be that top, y equals x squared plus 5. The middle one is going to be y equals 2x minus 1. And then the bottom one is going to be y equals -6. And then here is where we have to be careful about what x values we plug in. Okay, so I'm going to start with x squared plus 5. I am only allowed to use x values less than -3. But we talked about before, we don't want to start at like -2 because there's like a whole unit we're missing there. We get really, really close to -3, we just don't touch it. So like I want to include things like -2.8 and -2.9 and -2.99. So we put -3 there, but we make a little note to ourselves like, hey, it's going to be an open circle. We're going to get close to that point, but not touch it. Okay, that gives us that whole extra unit on the graph. And then anything less than -3 would work. So -4, -5, so on and so forth. Okay, and we'll plug those in later. 2x minus 1 can be anything between -3 and 4. I definitely need to include -3 and 4 because those are the breaking points we talked about. And then you can pick any other number. I'm just going to put a 0 in there. Okay. -3 is equal to, so it's going to be a closed dot. 4 is not equal to, so it's an open dot. And then the last one is defined for x values greater than or equal to 4. So 4, solid dot, and then anything bigger, so 5 and 6. Just keep it easy. That's the hardest part, I think, about this problem. Just making sure you got your table set up right, making sure whatever breaking points are listed next to each function are at least included in the table. That's like your minimum, and then you maybe want to include more than that so you get a good graph. Okay, so now I'm just going to take each of these x's and I'm going to plug them into the equation that they're next to. So this is where you would just, use your calculator if you need to. -5. -5 squared is 25 plus 5 gives me 30. -4 squared is 16 plus 5, 21. 3 squared plus 5 gives me 14. Okay. -3 into my linear equation. 2 times -3 is -6. Minus 1 is -7. If I plug in 0, I get -1. And if I plug in 4, I get 7. Now the bottom ones, there isn't a place to plug x in. So what does that mean? What are all my y's going to be? Yeah, that pretty much tells us, hey, it doesn't matter what x is, the y is always -6 because it's a constant line. We're going to see a horizontal line. All right, so let's graph these. I've got a few that are going to be kind of way off my graph here. -3, 14 is where the open circle is going to be, so I'm just going to kind of put a 14 up there. -3, 14 is going to be there. And then that graph is going to go forever to the left, so it's actually going to go like up there. Okay, you could always like count by 2s or something if you want to, but everything else will fit pretty nicely on here. So I'm just going to leave it like that. I know it's going to be that curve shape because I know it's a parabola, right? X squared plus 5, we should know what that looks like. It's our parabola that's just been shifted up 5 units. That's why it's so high, because we're just seeing that far side of it. Okay, the next one I know is going to give me a line. -3, -7 is a solid point. 0, -1, all the way up to 4, 7, which will be an open circle. Okay, and that segment doesn't continue indefinitely in either direction. It's contained between those two pieces. And then last but not least, 4, -6, 5, -6, 6, -6. And that one was defined for any value greater than 4, so that guy's going to go forever to the right. Okay, and then you can real quick do like a vertical line test and make sure it passes the vertical line test because this is a function. Are there any points where this graph is discontinuous? Discontinuous meant when we traced it, we had to pick up our pencil. If you remember that. Where do I have to pick up my pencil? At 2 places. Blair, which x values is it discontinuous at? Yep. Perfect. Okay. So what x values is it discontinuous? Now, if I had 2 pieces that kind of lined up and I didn't have to pick up my pencil, but just went from one to the other, I wouldn't consider that. But this is usually going to be your breaking points when in doubt. It's places where those inequalities are starting and ending. Yep.
If it lines up with a closed circle,
that would not be discontinuous. So like if I put, well, I don't want to do it over here, but if I put a closed circle here maybe, and I did that, like if I didn't have this guy, if I had that, it would not be discontinuous at 4 then. But because I had to go to another part of the graph at 4, that's what makes it discontinuous. Okay. Other questions on this one? All right. Moving on. All right, use these functions below to find all of these following things. So this is all the combining and composing stuff. So if you see it like this, you can also write it like this. Okay, it's just a fancy way of saying take function C and subtract function D. So that's going to look like 4x squared minus x plus 3. And then if we're subtracting something, parentheses are going to be important when we do our order of operations. 5x minus 1 goes in parentheses there. So the first thing I need to do is distribute my negative. 4x squared minus x plus 3 minus 5x plus 1. And then we're just going to combine together all of our like terms. So final answer for this one's going to be 4x squared minus 6x plus 4. If there's an x in the parentheses in your notation, your answer should just be a new function. It should not be a number. Okay, so we just created a new function by subtracting 2 functions, and then you don't go any further than that. You are not solving anything. All right, now the next one, actually I'll go down the row. The next one, letter B, is multiplying the functions by each other. So let me fill that in. 4x squared minus x plus 3 times 5x minus 1. So this is just a giant version of foiling. It's just telling us we need to multiply everything in the first parentheses times everything in the second parentheses. And I have 3 terms and 2 terms, so I should have 6 things if I multiply everything together. I'm going to multiply 4x squared by both things in the second parentheses. That will give me 20x to the third minus 4x squared. Then I'm going to multiply negative x times everything in the second parentheses. That's negative 5x squared plus x. And then I'm going to multiply 3 times everything in the second parentheses. That's going to give me 15x minus 3. And then again, combine your like terms. Final answer, 20x to the third minus 9x squared plus 16x minus 3. Okay. All right. Letter C. I like that notation with the double parentheses. If it looks like that, it's a composition where we're plugging one function into the other. Which function's being plugged into which? D is being plugged into C. All right, so 5x minus 1 is going to go into function c anywhere there's an x. Now there's two x's, so there are two places where you will be plugging that in. Please put it in parentheses. So that's going to look like 4 parentheses 5x minus 1 squared minus 5x minus 1 plus 3. All right, move it down a little bit so I have some room here. All right, and then we just have to simplify. Again, FOIL before you distribute. Got to bring that 4 down. If I FOIL out 5x minus 1 squared, what do I get? Well, 5x times 5x, 25x squared. My outside terms will be a negative 5x. My inside terms will be a negative 5x. That's negative 10x. And then negative 1 and negative 1 give me a positive 1. Bring everything else down. Now you may distribute 100x squared minus 40x plus 4 minus 5x plus 1 plus 3. And combine your like terms. 100x squared minus 45x plus 8. When I put all my like terms together. Okay. Any questions on that one? Okay, so again, there's an x in all of those, which means we're just getting a new equation. Back up to letter D now. Now they're actually going to start to get easier. Those were all the harder ones. So you can see it written with the open parentheses. Why isn't that erasing? It doesn't like me very much right now. I like to write it like this with the double parentheses instead because I think it's more obvious to see that C is plugging into D there. C into D. So that's going to look like 5. Take the x out, put that whole function in its place, 4x squared minus x plus 3, and then minus 1. So not a whole lot to do on this one. We're just going to distribute. No foiling necessary. Plus 15 minus 1. And then combine my like terms together. 20x squared minus 5x. Computer's being a little jumpy. Plus 14. Okay. Questions on that one? All right. Then we're going to get into the ones where there's numbers. These are just ones that you're doing calculations with. Okay, so this is telling me plug negative 5 into C, plug 4 into D, and then subtract those two answers. If I plug negative 5 into C, can maybe do that in our head? Maybe. Negative 5 squared is 25 times 4 is 100. Maybe I'll write that out. It's 100 minus negative 5, so plus 5 plus 3. Oh, come on, computer. Don't do this to me now. All right, I'm just going to do this on the whiteboard. I don't want to mess with that right now. Until that gets its life together. There we go. Minus, okay, I'm going to plug 4 into D. 5 times 4 just gives me 20 minus 1. And then just simplify a little bit further. Again, you could do all this at once if you want to. 100, 5, and 3. The first one's 108. 20 minus 1 gives me 19. So that's going to give me 87. It's going to be the final answer on that one. The bottom one, D of C of 1. Remember when we see this double parentheses composition? We're working from the inside out. So the innermost parentheses, C of 1. It's telling me plug 1 into C. Okay. If I plug 1 into function C, the first term will be 4 minus 1 plus 3. So 4 minus 1 gives me 3 plus 3. And again, you can use your calculator for that part, gives you 6. So now I'm evaluating D of 6. So I'm plugging 6 into D, which would be 5 times 6 minus 1, 30 minus 1, or 29. So those are a little bit simpler. You use those numbers. plug some things in the calculator and evaluate. Okay. Questions on that one with all the combining, composing stuff? No? Okay. All right. Number 7, find the inverse of the given function, then name the domain and the range of the inverse. Is my computer going to work now? We're going to find out. If not, we'll go back to the board. Okay. So remember, our function notation is a y. We're going to flip it. And we're okay so far. X's become y's, y's become x's. That's our first step in finding an inverse. Second step to finding an inverse is we start to get that y alone. Doesn't matter what it looks like. We're not looking for a certain form here. We just want to get that y alone. Okay, so I'm going to subtract 4. Then I have that negative in front of the square root. So I'm just going to either multiply or divide, however you want to think about it, both sides by a negative. It's going to flip all my signs. Negative x plus 4 equals the square root of y minus 5. Now you can square both sides. Put that side in a parenthesis squared. I'm not going to FOIL it out. You can FOIL it out. I don't think it's helpful. And you could make a mistake doing that anyway, so why not just leave it? And then last step to get the y alone, we're just going to add 5 on at the end. So negative x plus 4 squared plus 5 equals, and then at the very end, we don't want to say g of x, or we don't want to say y, because it's an inverse. So we want to write that inverse notation back in there. That's where the whole point on your test is just putting that inverse notation in at the end. Okay. Now, if I want to name the domain and the range of the inverse, I'm going to come back to the domain in a minute. The range of the inverse is the domain of the original function. And you guys did this on your test yesterday. If I want to find domain of this guy, I'm just going to take that x minus 5 and say, hey, that's got to be greater than or equal to 0. So x has to be greater than or equal to 5. That's my range, 5 to infinity. Now the domain is a little bit harder. What I would recommend doing, and you could actually do this to help you as well, is just graph this original function. You can make a table of values if you want, like we practiced. This one's got a lot going on with it. I know my x's have to be greater than 5, so I'm just going to use 5, 6, 7. Okay? If I plug 5 in, that square root's going to be a 0. 4 minus 0 is 4. If I plug 6 in, 6 minus 1, or 5 gives me 1. Square root of 1 is 1. 4 minus 1 gives me 3. 7 would give me a decimal. What would not give me a decimal? 9, maybe? Let's get a pretty whole number. 9 minus 5 would be square root of 4, which is 2. 4 minus 2 is 2. That's enough to graph it. 5, 4, 6, 3, 9, 2. Something like that. And again, that starting point is really the most important one. 5, 4. You can see in that picture that the domain is 5 to infinity. What's the range of that picture? What's the lowest that graph goes? What's the lowest that graph goes? Not the lowest. Does it go down forever? It's not an asymptote. It actually does curve down forever on a square root graph. Square roots don't have asymptotes. Negative infinity. It's going to go down to negative infinity. What's the highest that graph goes? 4. That's your domain of your inverse. The domain, and well, actually I should write it the other way. Negative infinity to 4. Okay. The domain of your original graph is the range of your inverse. The range of your original graph is the domain of the inverse. And you can figure out from the equations too, but sometimes the graph is just a nice way to visualize. Okay. All right, let's look at the next one. This one's actually a whole lot easier. That one had restrictions, which makes it a little tougher. So I'm going to switch the x and y. X equals 4y cubed plus 2. How do I get the y alone? Subtract 2. Then divide by 4. Again, I'm not trying to make this like pretty. I'm just going to do the whole thing divided by 4 equals y cubed. And then what? Cube root of that whole thing. And instead of y, h inverse. Does an x cubed graph have any restrictions? No. Does a cube root graph have any restrictions? Square root does, but cube root doesn't. So there's no restrictions in either of these functions. So my answer for domain and for range is all real numbers. You can graph them if you want to. It's going to go forever up and down, forever left and right. Yep. In past math classes, you use that notation. Correct. You must use this notation. Always interval notation for us. Yep. Okay, questions on that one? All right, last problem. Given a graph the new function with transformations. Okay, so we're going to look at the equation we're given up there and figure out what those numbers do. What does a negative on the outside of a function do? Reflect over the x-axis. Okay, good. What does that 0.5 or 1/2 inside do? Stretch, which way? Horizontal, stretch by how much? Not 0.5. This is a reciprocal, so 1/2. The reciprocal of that is 2. And then last but not least, we're going to move it, that plus 2 up 2. So we're going to physically move these points. If I were you, I would label these points to start. These points are 0, 3 and 3, 6 and 6, 0. Okay. The order that we do this in is pretty much the order that you see up here. Usually we start with a horizontal shift first, which is a left-right shift, which we don't have in this problem. If we had a horizontal shift left or right, you would do that first. Then actually your reflections and your stretches can happen at the same time. So we're good how we've got them listed there, and then up or down always happens last. This was kind of like the order of operations we had talked about. So left-right shifts, then stretches and reflections, then up, down last. Okay, so the first thing I need to do is reflect these points over the x-axis. If I flip something over the x-axis, how are those coordinates going to change? The y is just going to become the opposite, negative in this case. Yep. And you can graph it, or you can just list the points if you only want to graph it once. I'll leave like markers out if you guys want to do this in different colors, if that's easier on your test. 3, -6 is going to be down there. And then 6, 0 is actually on the x-axis. So is that going to change? It is not. Okay, and then you can see that reflection over the x-axis. Check. Part 1 done. Second thing I need to do is a horizontal stretch by 2. So horizontal is left, right. If I'm stretching it, I'm making it wider. Think about this like our taffy, okay? Now, this first point is already on the y-axis. It's 0 units away from the y-axis. So if I pull it twice the distance, it's still at 0. That guy's not moving. But the one at the bottom is how far away from the x-axis? 3. So we're going to multiply that by 2. That's what the 2 is. So we're going to double it and make it 6. Now you can see how it's starting to stretch that way. The other guy that's on the x-axis is 6 units away from my y-axis. So if I want to stretch it, it's going to move to 12. Best we can there. And you can see the horizontal stretch that happened. It's wider by a factor of 2. The last one's the easiest one. All we have to do is move it up 2 units. Up 2, up 2, up 2. And that blue graph is our final answer. If you wanted to list the coordinates of the blue graph, let's see, 0, -1 would be that first one. What's the next one? 6, -5. And then the last one was at 12, remember? 12, 2. So if I were grading it, that's what I would be looking for. I would be looking for, number one, that you're naming your transformations. Think of that as like the work you're showing for this problem. And then those final 3 points, okay, are how you're getting your credit on that. All right, there's a lot on this half. Lots of practice problems on Polaris for you guys to look at this weekend, okay? And I recorded this, so if you need to play back Mrs. McDonald telling you it again, it'll be on YouTube for you. Sound good? All right, so I'll do cell phone lotto. You got about 6 minutes left. All you're doing is just studying, and there's a Piecewise circuit training if you want a little extra practice on that. Okay, cell phone lotto winner. 27. Nobody's in. Thank you.